Okay guys, let's say that we want to add an R group now. Okay, so instead of chlorine or bromine or nitro or sulfonyl group, we're going to add an R group. So here's my R group right here. I'll just highlight it. So if this is my R group, I need a halogen on it, so that will be my leaving group. And it's going to first complex to the Lewis acid. And when it does that, okay, I want to just remind you back to this idea here, the reason how the catalyst works, or the reason why it allows benzene to react, is because there's this complex. So like the Br is going to do an Lewis acid-base reaction, and it's going to make what it's attached to more positively charged. So same thing here. What's going to happen is my R group's going to become that positive charge. So let me show you in maybe in red. I'm going to show you that these lone pairs are going to bond to the Al, and that's going to push the electron density this way, and it's going to make this carbon my positive charge. Okay, so I want you to think about that. Here's my positive charge, and then my benzene ring is going to attack that positive charge. So that's going to give me, okay, this kind of thing. And then I just need to regenerate my aromaticity then after I do that. So how to do that is I take this hydrogen and I'm going to regenerate the aromaticity. Now the only downside is you get rearrangement. Do you know why you would get rearrangement? Take a look at our carbocation. This is primary. That's not so great, right? So what's going on here is more likely there's some carbocation rearrangements going on, and this positive will actually rearrange to secondary carbocation, and then that's what gets attacked, and that's how we end up with the other product. So maybe I'll just show that reaction here. That attacks there. Then we end up with this kind of a product as well. So we end up with a mixture, and it's more likely to get this as your major product, not the straight chain, because of the carbocation instability here. We want a more stable carbocation. So that's a limitation of this Friedelcrafts alkylation. Another limitation is we tend not to use vinyl because that's an sp2 carbon, and we don't really like positive charges on sp2. It's too close to the nucleus. And then we also notice that if we have a nitro group on the benzene, we tend not to have any reaction with Friedel-Crafts. It's different with Br2. It will react, but with Friedel-Crafts it's more sensitive. So we see no reaction in these two cases. All right, so let's just practice. We want to make the products when benzene is treated with each of these alkyl halides. So that means the reaction is benzene plus the alkyl halide given, and AlCl3 then, and we want to know what do we make. Okay, so let's talk about this one. This one is secondary, so I don't think there's going to be any rearrangement. So then it's just a matter of this will complex with the aluminum, that will make this positive, and then the benzene ring will attack here. So what I should get then is something like this. All right, so that's my Friedelcrafts product. Okay, all right, so go ahead and practice these as well and see if there's rearrangement, and if there is, then show me the rearranged major product. All right guys, here for this second one, basically this is already tertiary, so I think we're good. I think we're just gonna attack here, and then that gives us a 1, 2, 3. Just puts an R group on there. This one I think is going to rearrange. Do you guys see that? So this is primary here, but it's tertiary here. So I'm actually going to rearrange it, I think. So I might end up with a positive here and then just do a hydride shift and get a tertiary. So what that reaction is going to be is this will attack the tertiary. I know it looks funny, and then we're going to regenerate the aromaticity again. Just make sure you don't have too many bonds. 1, 2, 3, 4. That one's okay. And again, that's because this is primary, but if I do a shift, I could actually make the positive charge more like here. And that's better because it's tertiary. It's going to be more stable there. All right, last question. Friedelcrafts alkylation is electrophilic aromatic substitution, that's the name of these reactions, in which the electrophile is a carbocation. All right, in previous chapters, we've seen other methods of forming carbocations, such as protonation of an alkene with a strong acid. So you guys remember, if I took that alkene and I had a strong acid, I just did that, I'm going to end up with a positive charge right here, okay? So if that's the case, then that is my electrophile, and I can react it with benzene as my nucleophile, right? So let's see, I'll just bring this over here. And then this can react there, and what I would get, there we go, something like that, right? So then I just need some kind of a base to come along and regenerate the aromaticity. And I want you to really focus on how do we get there? Like everything's the same, okay? We have an electrophile that's positively charged, and then we have the benzene attack it, and then the benzene's no longer aromatic, and we regenerate the aromaticity. So you end up with a substituted benzene. That's how all of those reactions work. So let's review some of those limitations again. For Friedelcrafts alkylation, when we want to add an R group, don't add one that's vinyl, so you can't have one with a pi bond there. You get rearrangement if you have a straight chain, so you want to try to always have the more substituted one. And then nitro groups on your starting material really slow down the reaction. See, the 3 limitations. Well, to avoid the carbocation one, we can actually do this modification. We have a Friedelcrafts acylation rather than alkylation. How that works is we have a C double bond O, not just the R group. Okay? And so what's going on here is if you picture C double bond O and an R, and the Cl is really with the Al, so let's say this goes over here, that makes this positive. Turns out there's a resonance delocalization, and so that group, even though it looks pretty unstable, it's resonance delocalized. And that's why it is fine reacting here with the benzene. So benzene is going to attack this positive charge right there. Okay? Or it could attack this carbon and then push the electrons out. Either way, it's going to attach to the carbon. It's going to attach to this carbon right here. So let's practice that. I have benzene. It's my nucleophile, and it's going to attack here. And so what I'll make is a benzene that's now got this group on it. It's an acyl group. And then I'm going to need to regenerate the aromaticity. Okay, so notice it's just like alkylation. The only difference is it has a carbonyl group there. All right, so this is called an acyl group. Now this is really useful because if I want a straight chain, I can't do it with the alkylation because it rearranges, but I could do it with the acylation, and then maybe I can just get rid of the C double bond O by reduction. So what do I need to reduce? I usually need metals. So here's zinc mercury amalgam, so it's this alloy of zinc and mercury with acid and heat, helps to get rid of a C double bond O. It's just gone. It's replaced with H's. Okay, so this is reduction. So start with benzene, show how the Friedelcrafts acylation plus this reduction called Clemmensen Reduction can be used to synthesize N-butyl benzene. So first, let me refresh why this doesn't work. And with Friedelcrafts alkylation. With the Friedelcrafts alkylation, the reason why this wouldn't work with alkylation but will with acylation is because if I had an N-butyl, let's say chlorine or bromine and AlCl3, 1, 2, 3, 4. Okay, let's say we have this. The problem is this is primary, so it's going to rearrange to the secondary, and then I'm not going to get the N-butyl benzene. So this is going to be more likely to give me something branched like this, some rearranged products. So basically, Friedelcrafts alkylation doesn't work on a straight chain R group because of rearrangement. Okay, so how do we use the acylation then? How we do that is we're going to use a carbonyl group in there, and then make sure we only have 4 carbons. And we're just going to do almost the same thing, but we're going to have a carbonyl group now. And then to get the N-butyl part, we just need to reduce that. So we're just going to get rid of that, replace it with hydrogens. Okay, and to do that, we need to do step 1, the acylation, and then add a second step. Step 2, Clemmensen Reduction up here. That's the zinc, mercury, and HCl and heat. All right, so that's how we do that. So identify whether each of the following can be made using the alkylation or the acylation with Clemmensen. So I think you can already tell which of these might be susceptible for rearrangement. It's going to be your straight chain ones. This is going to be rearranged because there's no way that I'm going to have a carbocation that's primary that this is going to attack. It's going to rearrange the secondary position. So these guys here. Well, actually, ethyl group is fine because it's going to be positive here or here, right? So it's going to be fine either way. But yeah, here this is primary, so this is going to be difficult. And here as well, this is primary, and I might have a methyl shift, so this would be hard to keep in its present configuration as well. Let's go through that. Let's look at A. So for A, in order to do Friedel-Crafts, I would have to have this kind of an alkyl halide with AlCl3. I'm using Cl, but you could use Br as well. And so what happens here is if I have a positive charge here after the chlorine leaves and goes to the AlCl3, this becomes positive, and then I could have a methyl shift. If I have a methyl shift, let's do this in steps, all right? It's too much. All right, let's say that the chlorine goes to the aluminum. Then that makes this group here positive here, but that's not stable, right? So we're going to move the methyl group over, so that R group is actually going to look more like that. And then this tertiary is where the benzene is going to attack. So I don't think I'm going to get this isopropyl group. I'm going to get sec-butyl instead. Or let's see, what is that going to look like? That's going to look like. Okay, so I'm actually going to get a tertiary there. All right, so for A then, it doesn't work, right? I can't do an alkylation. So for A, I'd have to say that I would want to do the acylation instead using this and AlCl3. And then I can really fix it so that it'll have this. And then I'll do Clemmensen reduction. And then I will end up with the final product that I wanted. Okay, so that's really the effective use of the Clemmensen reduction right there. And then here's a little bit of a lot of text here, so it probably looks a little scary, but let's read through it. It's probably not that hard. Friedelcrafts acylation is electrophilic aromatic substitution, and your E electrophile is an acylium ion. Acylium ion, what they mean is it's this group right here, acylium ion. Okay, so it's that carbonyl group, the carbon. There are other methods of forming that, just like using anhydride right here. The resulting ion can be attacked by the benzene ring, and you end up with this. Okay, so let's see if we can figure this out. I think you see that this group is this group. So I basically want to attack like that. So there must be something going on here where this group is being drawn away. And so basically I'm just coming up with these ideas. Okay, so AlCl3, that's my Lewis acid. This is probably getting pulled away to there. And then that means that this bond's breaking, and so I end up with a positive charge there. So positive charge there, and then I have resonance delocalization, something like that. Okay, so there's my resonance stabilized acylium ion, and then I have my benzene that can come in and attack that positive charge. Okay, so that's how I get this final product here eventually. So first I'll show the sigma complex. So this is on there, but I've got an H and I've got a positive. Okay, regenerate the aromaticity, and there I am. Okay, so all I did was I just had to figure out a way to make it positive here so that the benzene could attack there. And so this bond probably goes over to Al, and I make a Lewis acid complex with this. This is a Lewis base because it likes to donate electrons. This likes to accept them. All right, and next time we'll go over activators and deactivators.